To complete something, our main job in generally as an insurance company is to develop machine learning models that covers basically all the bases of the insurance company, ranging from life insurance, car insurance, of course, pricing, claims, and all these things. Today, however, we want to show you something a little bit different, one of our projects. And I'll start with a question. How many in the room know what this object is? Well, pretty good. Okay, for the people that don't know, this is a black box. There are several kinds actually. Sorry, I'll start with a brief agenda. Today we'll discuss then what a black box is and how we use it for a service that's called emergency call. In particular, we want to show you what happens if you are involved in a car crash. And then we'll show you what kind of approach we've taken using neural networks and what kind of drawbacks we found and how we are trying to overcome them. Finally, just to show you, because I'm the data scientist, I'm working on notebooks, not that real, but thankfully, this is not just a POC. We have this thing in production. So that's something that actually works on the black box of our customers. So let's start. First of all, a black box. It's a device that you mount on your car. There are several types. Typically, you have to mount it when you subscribe a telematic insurance policy. Generally, we have a sub-company called Geniot, which is specialized in the connected insurance on several areas, actually, mostly on car insurance. And they provide mobility services through the use of black boxes. Just to give you a practical example, if you're a Generali customer, a telematic customer with your car, you can benefit from several services, ranging from we analyze the driving style of our customers, and the best ones receive more discounts. That's easy. But one more interesting is how to improve their safety. And what we are talking today, as I was saying before, is a service called Emergency Call, which tries to improve the safety of a customer in case of a car accident. More on the black box. What's inside? It's basically a recorder device. It's also called event data recorder. It's equipped with several kinds of hardware, ranging from accelerators, GPS, and so on. We gather several kinds of data from it, and it's better if I show you exactly what the collected data looks like. And it looks like this. So you have, of course, GPS position. You know where the car is or where the car was when an event happened. And of course, you can say things like, okay, where did the event happen? Just to give an example. If you are put in contact with an operator, the operator must know where to find you and your car. We can tell from the data where the car has stopped after the event. And of course, we can say, okay, this is the speed the car was going. And then we can say, yeah, but after the event, the car has stopped completely. And of course, we can get accelerator data. As you can see, there are 3 axes of data, X, Y, and Z. All of these together, they can tell us how severe was the impact. Okay. Can we use this data to understand whether or not your car was involved in a crash? Okay, I was talking about this service called Emergency Call. It's basically a system that allows you to make a call, an emergency call to an operator. There are several ways to do that. One simple is that you have a button on your black box. So you just press it. There are kind of black boxes you mount on your windshield. There's a button you call for help. What we're talking today, however, is the automatic emergency call. So we get the data from the black box. We receive a signal with all the information that we've seen before. And we have to decide, is the signal worth to send to the operating center? can we send, what we do is that we receive the information from the black box and we process it in our systems, and then we send alert if needed to the operation center, where first a voice bot will call automatically the customer. If needed, a human operator will take the call and eventually send a tow truck if needed. Okay, this is good and all. This is a nice situation. The reality is this, where we have tons and tons of signals from the boxes, and I'm talking about 200,000 signals per day, where the actual accidents are luckily in the range of 100. And so if we had to send everything to the operation center, this would be the result, probably. So we have in our hands a very imbalanced problem. We need a strong filter, strong machine learning approach that filters out all the false positives, or most of them at least. Something that puts the operation center in, allows the operation center to actually work their real cases. So just to give you an example, what are these signals? Of course, we have the real accidents, but we also have potholes, device malfunctions, and so on. So here the real question: how can we decide if an event is to be sent to the operators? We have a baseline. We have people working in Geniot, people that are not scientists, but they know way more than me how a black box and a car works. So they can tell us how a crash looks like from the data. So they can tell us, okay, you have to look for these values, you have to look for these shapes, the speed should be something like that, the acceleration should be something like that. It works. As a baseline, it works. However, there are a few limits that we need to overcome. First, it's still a lot prone to false positives. That's something that you could, in theory, ignore, as long as the operation center is large enough to take all the calls. However, there's another real problem. As I was showing you in the first slide, the device is not one. There are several kinds of devices. Some you mount inside, maybe on the battery. Some you mount on the windshield. Some are even hidden everywhere. Some are mounted by people that don't know exactly how to mount a black box. So we have all kinds of behaviors in the acceleration, in the speed, and everything. So we need something that can be easily adaptable to all the different cases we see in our field. And moreover, the device, once it's trained, once we know it exists, unfortunately, we can't say in the next 6-12 months the behavior will be the same, because there may be firmware changes, maybe a new batch of black box will have a different behavior, maybe a different hardware. So we need to adapt. And what we try to do is, of course, apply a machine learning model, a deep learning model that can learn automatically from the data, which are the shapes, which are the values we have to look for. This is the typical approach in this field. We haven't introduced anything new here. We tried several approaches. The one we are showing here, it's based on a convolutional neural network. How many of you know what a convolutional neural network is? Most of the people, great. Just for people that don't know, it's a neural network that it's a deep learning model that's typically used to process images, videos, and so on. Just to say an example, to understand whether in a photo there's a cat or a dog. Here we don't look for cats or dogs, we look for crashes. But instead of looking for the ear of the cat, we look for the shapes that are correlated in some way to being a crash. So we treat that as an image, in this case at least. And we have, of course, great advantages. We have the CNN. We have a fast training and inference time, which is good, because of course this service should be very, very quick to help the customer. And of course, we have an increase of performance compared to expert-based systems. We have a main disadvantage, though. That's harder, way harder, to explain the results if someone asks you, why didn't you call me? I just crashed in a tree, for example, and you didn't call me. Why did the neural network told me that it was not a crash? And that's the main problem. We need to be able to explain the result for two main reasons. One is regulatory. As you probably already know, the AI Act is in full function since last year. So the European Union has set some rules we have to follow on which kind of models must have an explanation layer. This one is one of them. And not just that, we have a need to understand possible biases in a model, because there are, of course. The first training, you will always find biases in the result. So what we did in the last few years was to become partner of this European project called Human AI. It's basically a network of research centers, universities, and industrial companies. Generally, was the only insurance company in this project, and we worked together. The objective was not just find fancy things to publish, but was to work with universities to find new ways to make the models, make AI more explainable, basically. So what we did was work together with the University of Pisa and CNR, and basically we tried both existing methods and develop new methods to understand how a CNN reasons when dealing with multivariate time series data, such as the ones we are talking about today. We published 2 papers. If you want, you can take a photo. You probably already did. Briefly, in the last 4 minutes, then I'll leave more the rest to Angela. I'll just want to give you a brief overview of what kind of approaches we have taken. Let's start with the easiest one. Sharp values, you probably already know what they are. Basically, they quantify for each feature how much it contributes to the importance of the model prediction. It's very easy to apply. There's a very useful method called kernel explainer that it's applicable to all kinds of models. It's model agnostic. It's easy to apply also to CNNs. There's a main drawback here. It considers each feature as one time point. So it can tell us, okay, this instant is important for the network. Good for biases, not very good for explanation, let's say. So we tried something more complex. We tried a framework, a transformation framework called shapelets. They are basically time series subsequences found automatically by this approach. It tries to find in time series which are the recurring shapes that are mostly found in the data, and tries, of course, to understand which ones are more correlated to being a crash or not being a crash. In particular, what we did was to build a meta model that takes the output of the neural network and uses this basically as feature. There is this kind of shape, or there isn't, or maybe there is, but it's not exactly similar. And this becomes feature that can explain the results of the CNN. Here, what you do is, okay, this shape is important for the reasoning of the network. Major drawback here: good for human explanation, requires being a meta model, time consuming, and however, takes each time series by itself. It can't do multivariate time series yet. So what we did in the latest paper was to try to introduce multivariate shapelets. So we tried to do a new kind of shapelets that take into account different time series at the same time, because they are the same data basically, and try to understand which combination of time series are correlated with the reasoning of the neural network. You won't find that yet in standard libraries, unfortunately. But if you need it, I'll give you the link to the GitHub repository. And for the notebook part, it's all. So let's see how it actually works in production.
Thank you, Daniele. Okay, now I think we have a just little problem. How can we get this notebook work in production? So let's take a closer look to the architecture behind the crash detector system. But first, let's look at same numbers in order to understand the amount of data, the scale of data we are dealing with. Every month we have about 1 million devices, that is 1 million black boxes on the road, of which 400,000 devices send at least one alert. Every month, so generally systems have to collect about 6 million alerts, of which 50,000 sent to the operation center and 4,000 alerts are confirmed every month as real crashes, with 1,000 tow trucks sent by the operation center. Okay, now you have an idea of the large amount of data generally systems every month have to deal with. So how did we tackle this challenge? In the CDO team, we have as main tool in order to develop our projects the Google Cloud platform, and also the crash detector was developed using this platform. In this slide, you can see all the main tools involved into the crash detector architecture building, divided into two main groups: the tools involved into the main training phase and the tools involved into the inference phase. In the training phase, we have BigQuery as a data lake, then a Datapro cluster with PySpark in order to process the large amount of data collected, and the Vertex AI pipeline in order to actually build the model. The deep learning model will be used as input during the inference phase, where we have a little simple architecture, a bit simpler architecture composed of two pub/sub queues, one for input and one for output, and a cloud function that actually run the model. All the architecture is terraformed. All these tools are terraformed. As you know, Terraform is an open source framework that allows you to build and manage ET systems, ET architecture by coding, following the infrastructures code approach. Okay, let's see the training phase architecture. All the events coming from devices, coming from black boxes, together with the additional information coming from the operators, are stored, as we said before, on our data lake built on BigQuery. We are talking about millions of data, so that is several terabytes of data every month. This large amount, this huge amount of data, is then pre-processed by a PySpark cluster on Dataproc. Why PySpark? Because, as you know, PySpark enables efficient processing of large datasets by parallelizing computation across multiple nodes. So the result of this PySpark extraction, this PySpark computation, is the extraction of some features that will be used as input for the Vertex AI training pipeline. The training pipeline actually trains the model in our architecture by using TensorFlow, but the model can be trained using any framework, for example, Keras, for example, PyTorch, as you prefer. And the result of this step is the model, the deep learning model itself, that basically is a file deployed into a model registry in order to use it later during the inference phase. Okay. Here we have a diagram, a scheme of the Vertex pipeline, training pipeline, so the pipeline that allows to train the model and select the model. The process works as follows. Every time a new version of the model is trained, it is validated by a validation function. And then the result of this validation is compared with the validation of the currently in production model, so with the validation of the version of the model currently in production. If the current model keeps to perform better, it is kept in the model registry and so in production. Otherwise, if the new version of the model performs better, the model itself is converted into a TF-lite file, deployed into the model registry, and then it is used in production for the inference phase. We can start to use it. Okay. On this side of the slide, we have included a snippet of code with which we defined different stages of the pipeline. This snippet of code allows us to highlight one of the key advantages of using Vertex pipeline, that is, as you can see, each step is containerized, that is, it's run in its own container. This is an important feature because you can test and execute each step separately, independently from the others, and also, if you want, with a custom set of input parameters. For example, the training step takes as input a parameter that defines the GPU it has to use in order for its execution, but this parameter is not specified for the other component. Another key benefit of using Vertex pipelines is that each experiment you perform is easily traceable and reproducible. That is an important feature, especially during the output analysis phase. Okay, now we have collected and processed a huge amount of data, trained a new version of the model. How do we use this model in the real world? Okay. Here we have a schema of the inference phase architecture. It's a simple architecture composed of two FIFO pub/sub queues, one for input and one for output, and a cloud function that actually runs the deep learning model. It is clear that it's not a standalone architecture, but it is integrated into a bigger and more complex system, IT system. Okay, the process works as follows. The real-time event coming from the black box are sent via the queue to the cloud function. The cloud function runs the model predicts and attaches to the payload of the event some attributes, and then the output is published via on the output queue in order to propagate it to the rest of the system. What do the attributed, predicted, and attached by the model mean? These attributes allow us to understand if the signal, the alert coming from the black boxes, it's probably a real crash, so it must be sent to the operation center. It's an at-risk signal, or actually the black box is just spraying wolf, so the alert can be filtered out as a false positive. And so, thank you.
Well, thank you so much. It was really interesting. I don't see any questions on Slido. If anybody has any question, just raise their hand. Oh, maybe it's just my phone. I'm sorry. Can you say your question?
Hey, when you started off and you said like you have all the data from the black boxes and you turn that into an image and you use basically the neural network to analyze the image. Why do you turn time series data into an image to analyze it? Don't you lose a lot of information that way?
This is just one way to do that. Let's start with that. Yeah. It's not definitely, not necessarily the final way to do that. The scenario works though, because when you're talking about time series, like this one, like the acceleration one, you're looking for contiguous parts of the time series, small parts, that are suggesting in some way the presence of a crash. So let me give you a very simple example. A sharp drop in speed. So you pass from maybe 80 kilometers per hour to 0. That's a very specific shape that takes place in a very small part of the series. You don't actually lose that information in the CNN because you're actually learning a kernel that looks for that kind of shapes in the older part of the full-time series. So you can find, of course, the drop, the early part of the late part, but you just need to look for that particular shape. That's why the CNN, I think, they work. They're not necessarily the best way to do that. It works, it's fast. That was one of our requirements. We tried, of course, other kind of networks like LSTM and everything. But the main point that we wanted to discuss today was, okay, you needed to explain that, and that works for CNN, LSTMs, whatever.
Joining on this question, you mentioned that there were people in the company that were really experts on black boxes and accidents. So why not use this information with an if-else kind of
we did.
code?
We did for a while. Maybe we're still doing that apart. I can't go into messages, unfortunately, but that's definitely information that you need to take into consideration. So the CNN itself may not cover all the cases, for instance, but as a basis, it works better than just using the rules from the experts. But that's something you need to take into consideration anyway.
Okay.
So maybe, just to give you a brief example, you can put some, constructed features, special features feed into the neural networks as other information, maybe. That's in a way.
Okay. So the model works better than just if-elsing.
Yeah.
How another question? You mentioned finding biases. Did you just check for all the biases, or was there any way to detect them, like in outlier detection?
No, not directly, but what we did was to understand from the output of the shapeless and sharp values whether there were part of the time series that maybe we didn't want to be very important. Mm-hmm. So maybe, I don't know, you just cut them off, or maybe you change how you try to change what kind of data the CNN looks for. So that's the way we did it anyway.
Okay, thank you.
Any more questions? Okay.
Yeah. Thank you for the interesting talk. I have a question regarding the automatic training that you have offline. You use a validation set to assess if the model performs better or worse. How much often do you revise the hyperparameters? Do you do this automatically?
Automatically, yeah.
And do you revise also the hyperparameter space, or you just make a huge grid and you let the software choose which best hyperparameters work?
With Keras, I really like to use one of the tuners available in the library, Keras tuner library. So that's way faster than a grid search. So and that's you can the funny thing about Vertex pipelines, you can put inside whatever you like. So that's the part you can automate.
Okay, and the validation set is static, it's always the same?
No. Of course, if you have to retain that kind of model, you need to move the window every some time. And as Angela was saying, the issue here is that you need a long time frame of data, and that means taking terabytes of data in the training set, training validation tasks.
Nice, thank you.
All right, we have time for one last short question.
Okay, one question for you. Have you ever thought about bringing this algorithm to the edge? So realizing like a smart box.
Yes. Currently, as generally, we do not we don't make the black boxes. So we buy them externally. So that's not something we can do. That's definitely a way to do that anyway. Yeah. If we could filter them at the source, it would be nice. Yes. We can't.
All right. Thank you so much for your presentation.
Thank you.
And feel free to catch them outside if you have any more questions.